Hello guys, welcome to Recitation 8, which is RNN Basics. I'm Ewuze Chima Paul and I'll be moderating today's recitation. And today's recitation will be looking at recurrent neural networks and its architectures. So by the end of this recitation, we expect you to understand why RNNs are important even when we already have feed-forward networks. We would also discuss different variations on types of RNNs and their working principles. We'll understand how PyTorch implements LSTMs and finally be able to identify the variants of these RNN models. So we expect that the knowledge we gain from this recitation will help you get started with the homework 3, but we still expect you to do a lot of studies on your own as this is just the basics of RNNs. And of course, in the future, we'll do some other recitations that will cover more advanced concepts in RNNs and provide you with more tailored guidance in solving like in your individual assignments. Yeah. So one would ask, why do we need RNN since we already have like MLPs or feed-forward networks? Well, in so many tasks, as you will briefly see, there is always a need to remember previous information in order to decide or predict what is coming next. So feed-forward networks are not effective in remembering like past inputs. They focus solely on spatial information of the present input data and use that to make decisions. But RNNs, on the other hand, remembers the sequences in data and they are designed to remember or store information from previous inputs. So it allows them to make use of context and dependencies between different time steps. Um, for sequential data, the temporal information which connects the data is more important than the spatial content of each individual frame, which is why we subscribe to RNNs, which have like a way of modeling temporal information for this kind of tasks. RNNs have hidden states, which act as memory for storing previous informations. So we have been talking about sequential data, but now what are the sequential data? Sequential data is what we are trying to learn and predict using RNN, right? Now, sequential data like are streams of input data, where you have one input data dependent on another input data, is a kind of data where previous inputs play a crucial role in determining the next input. For example, in text or sentences, the current word to some extent determines the next word or the next set of words. We all know that we can't have is and was coming immediately after each other in a sentence. So that's some form of rule, right? Same with speech. We have word stress and pitch variations, which are expected to follow like a certain tempo while speaking. Even when analyzing videos, like in this frame here, we have that each frame in this video is sequential so that the model will be able to store this information, store the information of these previous video frames to predict what action is coming next. We also have the common time series data, such as the stock prices and weather data. We understand that for all these types of data, one needs to have an information about the previous input to potentially predict the next set of outputs. So where are RNN applicable? So RNNs are used under the hood for so many applications, right? Such as intelligent stock prediction system. Some of us are aware of trading bots. Some people use trading bots for trading stocks and also for trading like currency pairs. RNNs are also good in machine translation and speech recognition systems, where context is important in transcribing words or translating across different languages, right? They are also effective in video tagging and image captioning. Some research have also shown that RNNs are very good text summarizers, so they are able to understand passages and they create like summaries of them. Now moving on to the kind of structure of RNNs we use. So the structure or kind of RNN we use or we may consider to use for each task is dependent on the structure of the data, right? So we know that most feed-forward networks maps one input to one output. However, such constraints are not placed over RNN networks. Instead, their input and output can vary in length, and different types of RNNs are used for different cases. Like, so for example, we have like the one-to-one, which is known as the the vanilla network, generally used for machine learning problems, right? So where we have one input and one output. Here we have um here we have one input and one output, and it's an image of a dog here, and the input image of a dog will give an output of whether it's a dog or not, right? We also have one to many, with one input image and a series of word or sentences as output. Um, the one to many variant is a common use case for image captioning. So here, this is an image, and then the caption is a series of words or sentences, representing one to many. So we also have some other variants of RNN. So we have the many to one RNN, which is used for sentiment analysis. So when you have customer feedback and you want to do a customer review, so the customer review will have many words, and then your sentences, which is like a many input, and then our model will just tell us if it's a positive or negative review, which is one output, right? So there's also the many to many variant used for our machine translation, that is for transcribing from one language to another, which will be like many inputs and many outputs. You can also use many to many, right, for object tracking in RNN. So these are all like variants of RNNs, and depending on what you are predicting and depending on the nature of your data, you will likely use one of these one of these variants for training your model. So next, we try to understand the structure of RNNs and how they work or operate. So we have established that RNN saves temporal information, right? And however, for them to do this, they have to have access to previously processed information and use this in their prediction. So the RNN achieves this by saving the output, right? It saves the output from the previous hidden layers and passing it as an input to the next layer, including the original input of your X, right, to produce this Y. So it saves the output from the previous one, pass it as input, including the already existing input in the current time steps to produce your Y output. And that is why RNN network is often referred to as a looping network, right? The hidden layer in your RNN is equivalent to many hidden layers in an MLP compressed together. So the hidden layers in MLP are compressed together to give this one hidden state here in your RNN. So now this concept informs the notion of shared parameters across the hidden layers. Since they are compressed, we expect the parameters of the hidden layers each time step to be shared among the nodes or the hidden size of the RNN. So each hidden layer has like a standardized activation function, weights and biases shared across all the nodes of that hidden layer, right? Now, in learning the weights and biases of the network, RNN leverages a technique called back propagation through time, right? BPTT. This method is similar to the conventional back propagation, in that the model learns by calculating errors of across the parameters from its input layer to the output layer. Right, it goes from the output layer, that's the last layer, to the input, so it calculates the error parameters. But when you do back propagation through time, it differs from the normal back propagation, in the sense that it accumulates or sums the errors in each time step, right? So the errors in each time step as we go back is summed up or is accumulated, since the parameters of each time step is shared across, right? So it accumulates this error and use that for updating the weights and biases. So this is basically an unrolled version of the RNN network, right? Here we see clearly that the output of the previous layer forming part of the input of the next layer, right? And this hidden state H acts as the memory of the RNN of the RNN network. And also remember that this middle layer, right, this hidden state H can consist of multiple hidden layers, right, and each with its own activation functions, weights, and biases. Okay, so while we are discussing RNNs, it's also equally important for us to discuss the problems associated with RNNs. RNNs often run into two major problems during backpropagation through time. That is, as the weights and biases are being updated in the network. And this most times makes RNNs difficult or hard to train, right? These problems we're talking about are defined by the size of the gradient, which is a slope of the function along the error curve. Right? One of these problems is vanishing gradients. And this problem, vanishing gradient, occurs when the gradient, right, carrying information across the network becomes small, and with further update of these gradients, they become even smaller until they are finally insignificant and lose all information. Now, at this point, the network is no longer able to learn, so it no longer learns updates properly. So we can potentially solve this problem through careful weight initialization, through selecting the right activation, and also using LSTMs. We will discuss LSTMs shortly. Now, the other problem which RNN face is the exploding gradient problem, which is converse of the vanishing gradient. Right? So exploding gradient occurs when the model's gradient or slope tends to grow exponentially and becomes too large, thereby making the model unstable. Yeah. In this case, the gradient continues to grow very large until they are finally represented with a NaN value. Some of us might have come across this during training. This kind of error typically arises from the accumulation of large error gradients and updates across the network. Um, so we can try to solve this problem as well by using like identity initialization, using truncated backpropagation and the gradient clipping, right? So generally, to avoid these kinds of problems RNN, we must endeavor to store the right amount of information that we need for learning. So in the previous slide, we talked about LSTMs as a way of or a potential solution for solving vanishing gradient problem, which is like one of the most common problems in using RNNs. So now LSTMs is an efficient and effective way to deal with vanishing gradient problems in RNNs. LSTM is a variant of RNN, and they work to address the problem of long-term dependencies. Yes, they have the tendency to remember information over a long period of time, unlike RNN, which has a very simple structure. Like LSTMs have like a more complex structure, which helps them remember these informations. Now they both have like a chain-like structure, but the modules that form these chain-like structures are quite different. Yeah, the modules of the LSTMs have like gates, which control the flow of information through the network. We will discuss these gates more in the coming slides. Now, LSTM have different types, such as the LSTM Classic and the People Connection. We also have some other variant of RNN, which we'll also discuss later, which is called the GRA. Okay, so we first examine the classic LSTM. This is an image of a classic LSTM. Like we discussed earlier, the LSTM have gates, and there are three of them to be specific, and each of them performs a certain function in this LSTM model, right? Now, the forget gate, which is FT, the first one here, is a sigmoid function of the output from the previous layer and the current input, right? Now, the forget gate decides which information to omit or forget in the current time step. In the current time step. Now, there is also the input gate (IT), which decides which information to let through the current time step, right? And then finally, we have the output gate (OT), which determines how much information which currently resides in the memory makes it to this next layer, right? Now, across these gates, there are different variables like CT tilde, CT, and HT, and they are calculated using these equations that have been shown here. Now, the combination of all these gates in an LSTM allows the LSTM to retain important information from long sequences and discard irrelevant or outdated information. So another variant of the LSTM is the peephole LSTM, and this is very similar to the classic LSTM that we discussed in the previous slide. The only difference is that the sigmoid functions which perform these gate operations, right, does not just consider the output from the previous layer, ht-1, and the current input in this time step. Rather, it also considers the previous cell state, right? The information from the previous cell state in computing these gates, right? So ct-1 is added to the sigmoid functions in computing the forget gate, the input gate, and as well as the output gate, right? So and intuitively it makes sense because the LSTM have to know what cell state the previous cell is in before it tries to decide which information to retain and which information to forget, and finally before updating this particular cell state, right? So this is another variant of LSTM, and some RNN or some models use this particular variant in training some of their models. So let's quickly examine how LSTMs are being implemented in PyTorch. So NN.LSTM, so LSTM is a class or a function or a module, I'll say, in PyTorch, and it is implemented in this manner. So using NN.LSTM, we have different arguments for initializing this module. So we have the input size, the first argument, and this input size is the number of features in your sequence data. Then we have n hidden, which is the number of features in each of the n layers that are stacked. So it's basically the number of hidden features, right? And then we have the n layers. The n layers are just the number of layers for each hidden state, right? So when you have more than one layer, it's like stacking an LSTM on top of another one. Then we have the batch first argument, and this in this case is set to true. So if your batch size is the first dimension in the shape of your data, right? So you set this to true. So for example, here we have an LSTM cell, and on top of that, we have like a linear decoder, right, which takes in the number of features for one hidden layer and I suppose the size of one. So the network input size would be the would be like the batch size, the sequence length, and then the number of features for that input. And in this case, the number of features for this particular input will be one, same as this input size here, right? Now, your linear input your LSTM output shape will just basically be the batch size, the sequence length, and the output size. That will be like, because you're projecting to the LSTM, and then this hidden size will be the number of features for that particular LSTM. Your linear input will be a multiplication of the batch size and sequence. So for each batch size, you take a sequence, the number of sequence length multiplied by batch size. That will give you the number of inputs to your linear layer, and then it will be projected to the hidden size. And the same thing goes for your linear output, right? From batch size and sequence length, and it goes to your output. That's your final output size, which in this case is 1. So in the previous slide, we discussed how LSTMs is implemented by PyTorch, but it's important to take caution while implementing LSTMs with PyTorch, because it's important to consider like what shapes are the weights, what is the shape of the input weight, that's weight IH, or what is the shape of the hidden state, that's weight HH, and how do we even interpret these dimensions. Also, it is important to know like what version of LSTM that is being used by PyTorch, and also how do we even go about initializing the weights of LSTMs in PyTorch. So for this example, we have implemented an LSTM and printed the shape of the parameters here. So considering the way PyTorch implements the LSTM from the documentation, so this snapshot is from the documentation, PyTorch documentation. Each of these gates are calculated for each node of the hidden size, right? So for the input with IH, right? We expect a 4 by 1 weight dimension for each node, since we have 4 input weights, right? And in one computation, we have 4 input weights in one computation. And remember, the input maps to the hidden size, and there are also 4 nodes in our hidden size. There are 4 nodes, which gives So those four nodes gives the number of hidden sites. So when we stack this 4 by 1 for each node, right, we'll have a 16 by 1 shape. Like for one particular layer, we have a 16 by 1 shape. Also for the hidden weights, each hidden weight in the computation has a 4 by 4 size since it's coming from 4 input to 4 outputs. And so when you stack those 4 by 4 weights up, like stacking them up, you have like a dimension of 16 by 4. So that will be your weight. So your weight IH, that's your input weight, will be 16 by 1, and your hidden weight will be 16 by 4. Now the LSTMs implemented in by PyTorch is the classic LSTM, not the people. That is, it does not consider the current the previous state of the cell during computation. Can also check out the documentation, the PyTorch documentation for more detailed information about the shapes as we have discussed here. There is like a rubric and there is a rule for determining the input weights and the hidden state weights and their shapes as well. So do well to check that out, yeah, to get more information. So even as we consider the different variants and architecture of RNN, it's good to understand the trade-offs between the complexity, the components, and also the performance of these LSTMs, right? So we're discussing the performance per LSM component. So here we have we consider like different analysis that shows the performance of LSTM depending on the components which are included or not. So we had know that LSTM have different components like the forget gate, the output gate, and all of those. So we are comparing the error analysis to see, okay, without these components, which one performs better or which components are very crucial in improving the performance of LSTM. So for example, we see that we have the largest error size. That's this one here and this one here um, when using no forget gate. So when there is NFG, like so when there is no forget gate in an LSTM, it causes a large error, right, in the performance. Like so there is the error increases when there is no forget gate. And we can also see the same thing as for no output activation functions, right? So we see that some components of LSTM really affects the performance of the LSTM as a whole. So this slide basically just shows the different variations of LSTMs tested on different architectures and what the individual performance of these variants were. So now we discuss another variant of RNN, which is the gated recurrent unit GRU. This is the image or diagram or the structure of a GRU. Now, this has a simpler structure compared to the LSTMs and in turn lesser number of computations, right? In contrast to LSTMs, which have like three gates, we just have two gates in GRU, which are the reset gate RT and the update gate ZT. It also has lesser number of variable, just H tilde and HT. So it has lesser number of variable compared to the LSTMs. So generally, we expect the training time for GRU to be lower than that of the LSTMs. Right? So now let's see how GRU works. Now the RT, which is the reset gate, enables us to control how much information from the previous state we want to retain. Now, the GRU combines the input gate and the output gate of the LSTMs to form an update gate ZT. Now, the update gate ZT determines which information from the previous hidden state and the current input to keep. Right. Now, the final output of the GRU HT, right? The HT here, it considers what proportion of the previous state to retain and adds that to the proportion of information useful in this current state. That would be the HT tilde, right? And we see that here there are lesser number of equations and computations compared to LSTMs, and you also get comparable performance as well. Now, in fact, in some cases, GRU works better, and one of these cases where GRU and one of the cases where GRU actually lacks in performance is on unbounded counting. This is because LSTMs can count, but GRUs cannot count, right? And the problem is that because if you consider these equations, you see that the tan H equation, this tan H equation, right, the activation function H tilde, bounds the value of h, right? You pass the value of this h tilde between 1 and -1, and also because of this zt, you see this zt, using the sigmoid function, it bounds it between 0 and 1 since it's a sigmoid function. So when you use h tilde as zt in the calculation of ht, right, the values are bounded between -1 and 1, and that is why GRU find it difficult to perform unbounded counting, right? And whereas this is not the case for LSTM, since CT, so if you go back to previous slide, you see that CT is unbounded. So you can refer to the papers or the references below each of the slides to see the performance of the network when they encounter counting problems. So another variant of RNN is the bidirectional recurrence network, as BRNN, which uses future data for making predictions at the current time steps. Right? Now, as the name suggests, within this RNN, we have two directions of RNN. Right? We have the forward network and backward network, right? The forward network is represented by the network at the top of the block, and it processes value from time 0 to time t, right? While the backward network, which is the one at this bottom, processes so backward network at the bottom processing value from time t at infinity to time t at 0, right? Now, the final output of the block will be a function of both this forward net and the backward network. Typically, to get the output, we concatenate the output of these two networks, but alternatively, you can also aggregate them by either summing the values or by finding the mean of both of these networks, output of both of these networks. So, in the actual implementation of bidirectional recurrent neural networks, you can have stacks of BRNN blocks. Here we have three BRN blocks stacked on top of each other, and then an output layer, which is represented in this diagram by the yellow boxes. But instead of having this, you can also have like a single bidirectional RNN block, like this, the one here, but with the forward and backward network, each having like multiple layers. And in this case, it becomes like a bit more complex, and this backpropagation through time is also kind of complicated. So for the second part of this recitation, we'll be looking at an implementation of a language model. This will help reinforce your understanding of RNNs and models that can be built with RNN. So here we'll be using LSTM variant of the RNN, and here it's going to be a character language model. So we'll be given a set of characters, and the model will be to predict the next set of characters. So this, as you would have guessed, is a many-to-many kind of model, like many-to-many language model. So let's get started. So in this place, we are importing the models and the libraries that we'll be using for this for building this building this language model, and we're also importing our data, Shakespeare data. So for this model, we are using Shakespeare data for the training, and Shakespeare data is just basically poems and texts that were written by Shakespeare. So here we examine the characters and the structure of the data. We try to see what the characters look like. So here we have printed out the first 203 characters and the last 50 characters. And when counting the characters in this data, we see that there are like 55 million characters, and we have 84 of them to be unique, right? Now, the shape of the Shakespeare data is a column vector. So it's 55 million column vector, 55 by 1, right? And we have printed out as well the first 17 characters as indices. So these are the indices of the characters, of the first 17 characters. So each character has a unique index, right? So 84 to be 84 unique indices, right? So we now printed out the first 17 characters, right?
and this is how they appear. So even new line characters appear when you print the characters out themselves. But when you print the characters as text, you see that the new line is hidden. And one thing you should notice that this line and this line have variable lengths. So the number of characters in this line is different from the number of characters in this line. Just hold that thought, we'll come back to it, but it's important to note this, right? So the next thing we look at is the dataset class. This dataset class has three functions: the init function, the get item function, and the length function. So the init function helps us to initialize our data, right? So you pass an argument text and sequence length. And we have set the sequence length to 200. So text is basically the data, right? So sequence length setting just 200 just basically means that for each sequence, we want to take 200 characters. So for each particular sequence, we are taking 200 of this. So the way you have 55 million, so it's going to divide this into 200 different, like 200, divide each group. So each sequence will be 200 characters, each sequence 200 characters. And to get the number of sequences, since each sequence is going to be 200 characters, we divide the total length of text by 200. Now, self.data, I will just convert the text to tensors, and we have changed the shape to be a number of sequence by sequence length. So you're going to have the number of sequence which I've gotten here, and each of those sequences will be 200 characters for each of those sequences, right? So the get item basically gets each individual sequence from this data and returns that. So here we have the labels and the input sequence shifted by one. So now basically our input will be, like, say for example, you have to predict like the word or the text is computer. So basically you want to give the model a C so that it can predict an O, and you want to give it O to predict M. So your input will basically be compute, like COMPUTE, and then your labels will be OMPUTER. So what you're basically doing, you have shifted the text, the sequence, and the label you shifted this label by one step, such that the first character in the input sequence will predict the second character in the label, right? We'll predict the first character in the label. So for each input, it predicts the next character. So that's why you have done this shift here, right? So the length gets the length of the data. The collate function, I divide the collate function here. So it's receiving the list of sequences, and the collate function will help us to just create the sequences in batch, to produce batches from these sequences, right? And then we go to the language model itself. So in the language model, we have the vocab size, embed size, hidden size, number of layers. So the vocab size is basically the number of unique characters. That would be the vocab size, right? Which is 84 in this case, as we've seen up. Then the embedding size and all this, I'll discuss this as we go through these particular functions or modules. So nn.embedding, this is just like an embedding layer. So it takes in a particular set of text, there's the vocab size in this, and it embeds this. So what this is, projects this on embedding layer or an embedding space. So it's just like representing text in a vector space. So that you create like a vector representation. We know that vector representation helps us to store semantic information of the text, right? So once it's already been projected to the embedding layer, right, you pass that output embedded size now into your LSTM. So here, using an LSTM, you could decide to use a GRU, or you could, a GRU, right? And the input size to your LSTM will be the output from our embedding layer. And when you pass that, then you have your hidden size and number of layers. So giving number of layers to be 2, it will mean like 2 LSTM stacked on each other, right? And the hidden size will be basically the number of features for each hidden layer, or the number of nodes in each hidden layer. So that will be your LSTM. So the output from your LSTM will be going into your linear layer, which goes from the hidden size now, since it's coming out from the LSTM, to the vocab size. Since we are going to try to get the prediction across each of the vocab size. So we are predicting the probability of each character, and there are like 84 of them. So we predict the logits or the probability of each of those characters, right? And yeah, that's why it's going from the hidden size to the vocab size, right? And that will be your output. So in the forward function on the language model, we just pass in the batch. The batch will contain the length by the number of by the number of so to contain the length by the number of sequences, and you pass this to your self-embedding, and which will embed each of these sequence lengths, right? And once in a basis and represent it in and have like a vector space for it, you can pass this to your LSTM, and it returns it passes through the hidden, and then it goes through the it flattens it, and then it goes through the linear layer to produce an output size of the vocab size, right? The output to have like we have number of features equal to the vocab size, right? So after that, we have this generate function. What generate function does is like giving a number of sequences, it then it predicts the number of characters after that sequence. So sequence will be like the sequence you have given to it. The number of characters will be the number of characters you want it to predict after a given sequence. So we have the generated character, which we use to store our characters, an array where we store our characters. And so when you pass in the sequence, it covers it projects to the embedded layer to get the representation, and then it passes through these hidden layers of RNN, which is the LSTM in this case, and then it outputs this in the vocab size. So it outputs 84 different characters. That's what this sort of scoring output will do. From the hidden features, it projects it to the last layer, which is 84 different characters. And out of that 84 different characters, trying to get the maximum. And since they are going to be like probabilities, not like characters, going to be probabilities. And so you get the maximum, and that maximum, the character with the largest maximum, with the maximum probability will be the character that we are taking. And that will be appended to this array that we have set aside to keep our characters. So if the number of characters we want to predict is greater than 1, that means we need to pass in that predicted character, the initially predicted character, and predict the next character with it. So you go through the same process and take the maximum again and append that to generate the characters. So you do this for the number of characters that you want to predict in advance. So here is just our training function. Just most of you should be familiar with this. We use this in homework 1 and homework 2. So you have the criterion, and then you have your data chain loader enumerated. And for each time, you put your inputs and targets to device, and then create your model and use the criterion to get the loss. And then you do your backward propagation and optimizer steps. So the same thing with your validation function. So here we have just initialized the language model, right? So we've initialized the language model. So character count, this will be the number of vocab size, which is 84. And 256 is the embedding layer. 256 again is the hidden layer. And 3 is the number of layers. That will be the number of LSTM that should be stacked, right? And then we move this model to device. This is just created the model, move it to device. Then we have set an optimizer, and we're using another optimizer. And then we are using a split of 5 million, right? So we want our training data set to be from, I think that's 50, is this 50 million? We want our training data using this split. We are splitting our data set. So we're splitting our data set. The first set will be for training, the second set will be for validation. So now we pass in the train data set into the data loader, and we use our collect function to make batches of this data set, and that's our train loader. The same thing for our validation, right? So next thing we just do is to train the model. We are using 5 epochs here, and you can see the output, and we have trained this model just using our 5 epochs. So what we did was to write the function that will help us generate these predictions. So basically, you pass in the model, the seed is the sequence you are giving the model, and the number of characters is the number of characters you want it to predict like into the future. So you pass as tensor, then to device, and then you call model.generate. Remember, we have a generate function inside our language model, right? And it takes in the sequence and the number of characters we need to predict, right? And so here we have called this model, we have called this generate function, and we are printing it. So we have the model, and the sequence we are giving it is to be or not to be. That is the Q. So we needed to predict the next 8 characters, and it predicted this UESTION. So now this will be to be or not to be. That is the question, which makes sense. That's one quote of Shakespeare. It's a popular text by Shakespeare. So we have also done the same thing with this Richard, and then we want to predict the next 1,000 characters. and it has predicted this. Not sure it really makes sense, but that's the prediction of the model. So one thing I would like to discuss before we end this recitation is pack sequence. So you can go through this code. But what I wanted to just mention is that pack sequence helps us to use sequences of variable length. Like the way we use here, we use basically just a fixed sequence of 200. So our sequence length is 200. So each sequence has just 200 characters and it is fixed. But that can cause us to lose information in the real world. So for instance, if you have an example, the dog is running down the road and you make your sequence length to be like 15. So that will not capture the whole sentence. That will basically capture maybe the dog is run and leaves out the ing and other things like in that sentence, thereby limiting the semantic information which the model can capture from that sentence, right? So, but we all know that we cannot get our sentences and our sentences to be of the same length. So there will be like some kind of variations in the number of characters or words in a particular sentence. So to circumvent that, what we can do is to use packed sequences, which is a method that PyTorch has and it can be implemented. So what we do is we will not set any particular limit or any fixed number of sequence lengths. What we do is to just take sentences and for each batch, PyTorch will just pad the remaining sentences, which are not as long as the sequence with the longest length in that batch with zeros. So what you do, so imagine the longest sentence in a batch is has like 20 characters. Every other sequence that not up to 20 characters will be padded with a zero. With that, we still retain the uniformity in the number of sequences, but some of them will be padded with zeros. And with that, we can retain like semantic informations in each of those sequences, right? Before we can use it for training. So this is a very important concept, and you should definitely look at the code and try it out yourself. Yeah, so thank you guys, and with that, we've come to the end of this recitation.